supposed to be an effect of the proof of this theorem, that for every C, which is CE, not computable, there exists an A which is simple and C does not Turing reduce to A. So if you're interested in simple sets, you can find them outside of any upper cone determined by a CE set. And right, we had our requirements already. A co-infinite, or really the co-infinite requirement is usually best looked at as saying, okay, look at this movable marker construction, and then the eth co-infinity requirement says that the eth movable marker has to come to a halt, and the way you get the eth movable marker to come to a halt is to restrain everything below and equal to this eth movable marker from entering A, and so that's a nice finite restraint. We have the NE requirements, which say that C is not equal to phi EA, and this is the requirement that is sort of the novel one. When you see this first and you don't think about it for a moment, and then the Friedberg-Muchnik strategy jumps in your mind. Take something not in C, wait until the computation converges, and then put it in C and protect the computation, except, of course, in this case, C is given by the enemy. Right? We are in control of A, the enemy is in control of C, so they can do with it what they want. Which is why we came up with this other strategy, and the other strategy was all built around the length of agreement and the restraint introduced by this length of agreement. So the length of agreement that stays S really is look at your current approximation for S, for C, look at your current approximation for A, do all of the computations up to at most S steps, and see what sort of initial segment of C and A agree. And the length of agreement is the biggest number, such that for everything strictly smaller than it, the things now agree. And then the restraint that we imposed on this was, okay, for everything strictly less than this number, we had these computations converge on the A side, and we want to protect all of these computations, plus one more in case it converges. Well, in case it doesn't converge, then the restraint is automatically 0. So this is the maximum of the uses of A for X, for X, where X is less than or equal to the length of agreement. And the final requirement we had is, of course, the usual simplicity requirement, PE. If WE is infinite, then WE intersect A is non-empty. And here again, the strategy is just, okay, wait for something to appear in WE. If it appears in WE, stick it into A. That's sort of the basic strategy. Then you want to make it act nice with respect to the other requirements. So first of all, you say, okay, wait for something to appear in WE. Maybe accidentally already the intersection is non-empty. So you wait for something to appear in WE while the intersection is empty. If the intersection is non-empty, requirement is done and you don't do anything. Now this strategy is bad because it could still injure higher priority requirements. Therefore, this module is changed into saying wait for something which is larger than the restraint imposed by all the higher priority requirements to appear in WE while this intersection is non-empty, and then you enumerate this thing into A, and you're all set. Okay, so first we proved. So how does this whole strategy now act? Right? The whole strategy acts, and maybe I should write it out a little more carefully. Right? H naught is empty, and then at stage S in the construction, or at stage S plus 1, I guess this is probably stage 0. So at stage S in the construction, what you do is you do everything that is associated to requirements R naught up to RS. Right? I didn't say it, but here we have countably many requirements. Order them in some reasonable way in order type of the natural numbers, so that everything has finitely many requirements before it. The requirements in this new ordering are called the R requirements. And at stage S plus 1, you're going to take action on behalf of requirements R naught up to RS. And for each of these requirements, you run the basic module. And so that means that for R naught, well, if R naught is one of these co-infinity requirements, you check where is the 0th marker currently located, and then impose the restraint on the other requirements by this 0th marker location plus 1, that's the restraint. If requirement R1 is one of these requirements, then at this stage you again compute, with S being the stage, the current stage, you compute the length of agreement and the associated restraint, and you impose the restraint on everything else. If R1 is a PE requirement, then you enumerate WE for S steps, see which elements you have, and see if one of these elements is greater than all the restraints imposed by the higher priority arguments, and you check if WE currently intersects A in an empty way, and if both of these things are true, right, all of these things are still computable kind of things to do, then you enumerate X into A, and you've defined a new AS plus 1. And then you go to stage S plus 2, and now you work on requirements R naught up to RS plus 1, and you again run through the whole list. And this way you take care of more and more requirements. Okay, so then we need to see it works. So we want to see that C is not equal to phi E of A. And we do this under the usual assumptions that all of the higher priority arguments, all of the higher priority requirements achieve what they set out to do, act only finitely much, and have all of their restraints stabilize. And that's sort of the standard kind of lemma you want in this context. For this requirement, right? This is requirement NE. For this E, look at the collection of all of its predecessors. With induction, presume that they do exactly what you think they should do, and their restraints stabilize in exactly the way you think they should stabilize. I think you think, all of you are reasonable people, you're going to think the right thing, and so you know it's you know which lemma I just didn't state. And so under all of these assumptions, this the associated strategy NE is going to get injured only finitely many times, so look for a time t such that after this time it'll never get injured. Now what does it mean for requirement NE to never get injured? Well, it means its restraints are always respected by everything, which means that as soon as you see this length of agreement, then the A side of the length of agreement is permanently preserved, never ever changes, and therefore, if we work under the assumption that these two things are equal, then we can compute what happens with C by looking at what happens to a sufficiently long stabilized A side. And under the assumption that these two things are equal, the length of agreement goes off to infinity, and therefore there are these sufficiently long stabilized A sides. And what does the argument show? The argument shows that if these things are equal, and the requirement is the restraints are respected and everything, then C is computable, contradicting our assumption that C is not computable. Therefore, these two things are different. Okay, so in the inductive argument we have now done half of the requirement, or half of the things for the any requirement. Now we also need to see that, okay, this requirement, if it doesn't get inserted, which we could presume by induction, then it is satisfied. But then we also need to see that now its restraint stabilizes, because if its restraint does not stabilize, then the lower priority requirements don't have the room to work. Right? This is the whole point with these restraint functions. If the restraint gets too big, then you could maybe hope, okay, this restraint goes to infinity, but the next requirement acts quickly enough, but you can't act quickly enough because your speed of action as a requirement is not determined by you. It's again the enemy, right? It's the enumeration of WE which is not in your control, and therefore it's right, the enemy or the opposition enumerates these things. And therefore you can never hope that this enumeration goes quick enough for you to beat a restraint that goes off to infinity. Because if this restraint function, it's computable at any time, and therefore if it goes off to infinity, then there is a CE set that waits for it to go sufficiently far and then enumerate something small, and then wait for it to go again sufficiently far and enumerate something small. So the enemy can make a set that defeats you if your restraints go off to infinity. And because the enemy could make it, it already exists, and so you lose. But now, right, we have proved that these two things are different. Well, if they are different, then there is a least difference. Right? So there is an x which is least such that Cx is not equal to phi a e of x. So how can this happen? Well, first of all, everything smaller than this x is equal. Therefore, you can go to a time which is sufficiently far out that the length of agreement is at least as big as x. And moreover, all the computations done by phi e up to this length of agreement agree with the final computations that will be done. So at this time, one of two things can happen. Right? The Cx side is always determined to be 1 or 0, but the phi e side, the A side, might diverge or might converge. So if it diverges now, it could forever diverge, which is okay, or it could at some point start converging, in which case we go out to the time where it converges. And the time we've just now found, right? So this time t, which is the time after which the final length of agreement has been achieved and the A side converges, if it ever does. At that time t, we achieve our... Oh, one more thing needs to happen. Also, Cx should be equal to 1 if it ever becomes equal to 1. Right? This is whether x is in C, So this should be equal to 1. If you are at a time t which is past all of these things, then RET, the restraint has stabilized. Right? It's not going to get injured anymore, and it imposes the restraint, so the A side has completely stabilized, as far as it is going to stabilize, and the length of agreement will never be longer than the current value, because you've gone far enough out that whatever is involved in the computation of this first difference is already there. And so that shows that the restraint stabilizes to some, right? This is stabilized at some finite permanent value, and therefore our induction hypothesis for what we want by induction for this requirement has been satisfied. It satisfies what it's trying to satisfy, and its restraint is finite and bounded forever, and therefore by induction we've completed our inductive obligations. The other two requirements, co-infinite and PE, the proofs are exactly like the ones before. Just go sufficiently far out and it's all good. Good. Questions? Well, then we'll do this. At some point we saw that given a CE non-computable set, you can split this set into two CE non-computable sets whose disjoint union is exactly the set you started with. Now we're going to improve on this a little bit. If we have two CE sets, and C is not computable, then there are low CE sets A0 and A1 such that A0 disjoint union A1 is equal to B, and C is Turing reducible, is not Turing reducible to AI. So we can take this B, split it into two parts, and these two parts can be stuck sufficiently low in the Turing order that C can't be computed from it, while at the same time making them low. And this proof turns out to be a little bit surprising construction, I think. Well, the requirements are easy enough, right? If X appears in B, then X should go into one of the two A's. As soon as you find a new something appearing in the set B, you should put it in one of the A's. It's not entirely unimaginable that you might gain something by waiting a little bit, but it's very hard to imagine how you could gain by waiting a little bit, because just like here I said, these WEs are given by the enemy. Well, our enemy gave us C, and C could wait until we do something with an X, and then do something inappropriate for us. And so in that sense, if we try to take an X and we wait until something nice happens, or until we are sufficiently confident that a certain something is not going to happen with C. Well, it could be that C is looking at us until we do something with this X and then do it. And I mean, that's nothing like a proof or anything, but it is a heuristic argument for why it's unlikely to help waiting in this case. You see this X appear, you might as well make up your mind right away, except if there is something exceptional that you can do with it. And here is not the case. Also, in the I, C is not computable from phi e AI. But C should not be computable from either of the AI, and therefore we have these requirements that say that you're not computable from either of those. So now you say, okay, with this, okay, you haven't said anything about them being CE, but of course CE just means that we need to do our construction in the usual way, do computable stuff every now and then, decide to stick something in A0 or in A1, and then you get CE sets. Lowness, it appears I've said nothing about lowness. Well, lowness is going to follow accidentally from the way we're going to attack these requirements. So it's not necessarily in these requirements, but the way we're going to do these requirements is going to suffice to show that the sets are automatically low because of it. Okay, so what do we do? Well, of course, as usual, until it happens that we come up with a really good argument to start with something else than the empty set, we're just going to start with the empty set. And then at stage s+1, maybe I should have introduced these functions first, but we have these requirements. C is different from phi computed from A, and this is very similar to what we had before. And so in the same way you can define length of agreement functions, which say that well, the thing computed from AI using Turing machine E at stage S looks like it agrees this far with it, and then a corresponding restraint. So this is exactly like before, length of agreement. You say these are the length of agreement paraphernalia. But now, of course, you notice that, or you should be a little bit worried now, because I'm introducing length of agreement, and you know how a length of agreement argument goes, or at least the one we just did. That is, compute length of agreement, impose the restraint. But right? Why did that work in the previous argument? Because we got to pick x. Right? We had a WE, which if it was infinite, we needed to do something. So if it is infinite, then at some point the restraints of higher priority things stabilize, and then if it's infinite, something bigger is going to appear. But now we don't have the luxury of waiting for big things to appear. As things appear in B, we need to deal with it. Which makes this length of agreement idea a little bit, apparently a little bit out of place. Certainly the strategy can't be like before, where you compute the length of agreement and then impose the restraint, and then hope for the best, because it's just not quite going to work out. Okay, so what happens? At this stage s+1, we can compute all of these functions, and just like before, you compute all of these functions for, say, the first s requirements, for the first s of these, ordered in some way. This p requirement is a global requirement. doesn't have something specific associated with it. We order these in some way. For the first S of them, we compute the lengths of agreements, we compute the corresponding restraints, and then we compute the next thing that needs to go into B. And so we have an X which just went into B, and we need to decide, does it go into A0 or into A1? Okay, so this is the strategy, and what we do is look for the least NEI. Least NEI means highest priority NEI that would get injured. Maybe nothing gets injured, but if nothing gets injured, stick it into A0. Right? I don't care. If you want to be more equal opportunity about it, stick it sometimes in A0, sometimes in A1. I don't care. If nothing gets injured, stick it wherever you want it. If there is something that would get injured, then look for the highest priority requirement that would get injured, and then put X into A1 minus I. Right? This I is indicates which side you're computing from, and so 1 minus I is exactly the other side. So what we're doing here is we're just looking for the highest priority requirement that would get injured, and then we stick it in the other side. But if we stick it in the other side, this requirement doesn't get injured, which is good. Something else might get injured, but that something else has to be a lower priority requirement, because this is the highest that could possibly get injured. Right? If enumerating it into the other side would injure a higher priority requirement, then that would be instead the highest priority requirement that would get injured. So this strategy is built exactly around the idea. Look for the worst thing that could happen, and then if you enumerate it into the other side, still terribly bad things might happen, but not quite as bad as this highest priority one. This is the whole construction. And again, notice that indeed it is of the form, do computable stuff, and as a consequence of this computable stuff, every now and then decides to enumerate something into one of the AI. So whatever this does give us CE sets. It also gives us that A0 disjoint union A1 is equal to B. Right? For every X that appears in B, we immediately stick it in exactly one of A0 or A1. Therefore, this disjoint union requirement is also satisfied. And now we need to see that it works, right? That the length of agreement is bounded. Okay, so we want to see that C is not equal to phi AI of E. And again, presume that all the higher priority requirements have done their things, aren't going to be active, the restraints are stabilized and everything. Well, but of course, this is going to go the same way as before. If this requirement is never going to get injured again, then exactly as the analogous argument we gave here for the previous proof, if it's never going to get injured again, then the A side, as it appears, is always preserved, and if they are equal, then the length of agreement goes off to infinity. And if the length of agreement goes off to infinity and the A side never changes after the length of agreement has extended past some point, then you can compute C. And because C is a non-computable set, the length of agreement cannot go off to infinity, therefore the length of agreement is bounded, some finite value. Go a little bit further until maybe this one more place on the A side converges, and then you have the final value of the restraint. I think I said that all right. Otherwise you should object. All I'm saying is the same argument we gave before. Go sufficiently far out until the C side has stabilized far enough, the A side has stabilized far enough. Look at the length of agreement. That is going to be the final length of agreement. Maybe this one more thing on the A side will converge, which will jump up possibly the restraint once more, but that's then the final value of the restraint and nothing more is going to happen. So they really are different. And if they really are different, then we argued just like before, the length of agreement has this finite bounded value, therefore the restraint function is this finite bounded value. I just said this, right? And therefore it imposes only finitely much restraint on everything above. Well, imposes finitely much restraint on everything above. That's not quite how our construction goes, right? But the final value of the restraint is finite and permanently achieved at some point. And so how do you now find a time where the next requirement, which corresponds to the opposite set possibly, never get injured anymore? Well, this restraint RIES is equal to, I don't know, R is final and permanent value. Then as soon as BS restricted to R is equal to B restricted to R, right? As soon as B has been enumerated far enough out so that this initial segment corresponds, well, as soon as this happens, and that's the final value of the restraint, then past this time S where this happened, requirement NEI is never going to be injured, because the only things that will appear in B are past its restraint. So then you have progressed one more step where you have one more requirement that will never get injured, and therefore the highest priority requirement that might get injured by this X that you find is never going to be this one, and therefore you can move on to the next requirement. And also, past that time where this happens, this requirement is never going to be the cause for just enumerated into the other side, so it's not going to injure other lower priority requirements anymore. And therefore, the injury sets associated to this requirement are also finite. Say about it? There's essentially only this one nil part to the argument compared to the previous argument. Right? The fact that if you have argued that the restraint stabilizes, then from this you can say that there is a time where this thing never could be injured anymore, and therefore you move on to the next thing. In some sense, that's the only new part in the argument. Okay, then we can be all satisfied with ourselves, except for the fact that, of course, the theorem says low, and we haven't done anything about low. Apparently, we haven't even attempted to do anything about the lowness of these sets. So the final thing we need to argue for this theorem is that A0 and A1 are both low. That somehow in our construction this lowness follows. How do we do this? Well, we define a functional phi of GE on an oracle X on input Y. We define it to be C0 if Y is 0 and phi EXE converges, undefined otherwise. Now this is of course not a choice to make this undefined, because trying to decide whether this converges or not is something. You start the computation, if it ever stops, then it stops and you're good. If it doesn't stop, then you automatically have to be in the right outcome for this. Then you could be a little worried about this C0, because C0, right? What do we know about C? It's a CE set, so deciding C0 means you start the computation and either it stops or it doesn't. But that's not entirely true, because it's just this one value of C I need. So I don't need to compute this one value for C. I have C given to me by the opposition, but C0 is either 0 or 1. It is one of these values, and so I can just stick that value in here without having to compute it on the fly. You can do that because it's only one value you care about, so you don't have to worry about computing it. So this works out. So I argued that this function G is a computable function and gives rise to this computation. Okay. So what do we need to see? Well, we need to see that AI jump Turing reduces to 0 jump. Right? 0 jump reducing to AI jump, I'll leave to the reader. Always true, right? Therefore you don't have to do anything. So we just have to see that this jump is not too complicated. How do you show this? Well, a priori it looks like you should come up with a Turing reduction, but we're going to do it a little different. Because we have a nice characterization. Something Turing reduces to 0 jump exactly when it's delta 2. Right? And delta 2 meant limit-wise computable. So we have this strategy. It's enough to show that it's in delta 2. And how do you show something is delta 2? Well, either you can come up with a sigma 2 and a pi 2 expression for it, or you show that the thing you're looking at is limit-wise computable, right? That we want to say that E is in AI jump if and only if a limit is equal to 1, and this limit always exists. Right? I was going to try and figure out what the 0. If this limit always exists, of the limit of a computable function, we need to show the existence of a computable function such that the limit to infinity always exists and it's equal to 1 exactly when E is in AI jump. That's exactly one of our characterizations of being delta 2. Right? This now works out pretty well. Phi E AI of E converges per definition. What does this mean? Well, this means this definition of the function G was not entirely necessary. It means that phi AI G E of 0 is equal to C0. Right? These two things are equal exactly when this thing converges, and otherwise it diverges, and therefore they're not equal. So they're equal exactly when E is in the holding problem, and this happens exactly when the limit over S of Li G E S is greater than 0. Right? If these two things are equal, then the length of agreement is at least 1. If these two things are different, then the length of agreement is exactly equal to 0. And here we have Li is a computable function, G is a computable function, and so we're looking exactly over the limit as goes to infinity of some computable function having this property, which is exactly what it means to be limit-wise computable, and therefore we are in delta 2. So you see that really the lowness of this thing is encoded into some length of agreement, and therefore it just kind of accidentally happened on the side. Notice that it's not one of our requirements that gives it, it's the strategy for solving one of the requirements that gives it. Right? If we come up with a different strategy for P and N, then it won't necessarily automatically follow that we get M low. It only follows because we have this length of agreement strategy, which we can abuse here. Okay, so with that, I want to just say one more thing. Okay, we have these length of agreements to try and avoid upper cones for CE sets. And in our arguments, we use very much that C is a computably numerable set. Right? What does it mean? That as soon as you have phi E of A of something computing a 0, then as soon as C changes to 1, these two things are forever different as soon as you protect the A computation. Now, if you're looking at a C which is not CE, but just delta 2, right? What is it meant to be delta 2? Well, limit-wise computable, or sort of a more dynamic picture maybe, that right? A CE set, everything starts out not in the set, and every now and then you put something in. In a delta 2 set, everything starts out not in the set, every now and then you put something in, and you take something out again, and something this way can fluctuate just finitely many times. In particular, it means that right, you have your length of agreement, and then if C changes to become different, then that doesn't mean that the final length of agreement has shrunk, because C can change back again. And so what you want to do is, if you want to have a result where you conclude that some A you've constructed is not in an upper cone above C, what you have to do is not just measure what is the current length of agreement, but you want to measure what is the length of agreement now or in the past. Because any past length of agreement can start reoccurring again because C changes back. And that exactly works by saying that then the length of agreement is equal to the maximum of the length of agreement of earlier stages. And this is something which is of course greater or equal than the old length of agreement, but it's just, it has built in this idea that C might change back to what happened at those times, and therefore you want to protect those A computations as well. And then if you sit down and you go through the arguments, you see that it all works out exactly as it should.